want to know is, why does this mean that it's going to have a maximum speed? Well, let's think of an example of something falling. So let's draw a circle here, make it nice and neat. So this object, so we know how air resistance works now. We want to know why would that produce a maximum velocity or maximum speed? Well, the reason is, if we take an example of something falling, the constant force, remember the constant force pulling it in one direction, the constant force in this case would be the weight. So we can label that force as just mg, because the weight is equal to mg, but generally speaking we just write mg, so let's leave that and just write it as mg. Now at the beginning the velocity is 0. It's about to start moving. It hasn't actually started moving yet. It's about to start moving. Okay. So the resultant force, the total force, we're going to put Ft for the total force, is just equal to mg. Right? So then we have, in fact, let's just group that, and we'll say that's stage 1. So we'll call that stage 1. Then stage 2. Stage 2, it's now moving a little bit. So let's say velocity is small. It's moving, but it's just started moving. Okay, so it's got a little bit of air resistance, or a little bit of, well, it's an object falling through air, so this is air resistance, but you can still use the word drag, of course. Velocity is small, and we're going to call this resistive force. Well, let's call it D for drag then. So now that the total force is mg minus d. So we can see that it had the maximum force at the beginning, right? And then after a while, now the total force is less than it originally was, because the mg is still the same. It still weighs the same. It's still got the same weight, but we have to subtract the drag that it's now experiencing. Yeah. So we'll group that, and we're going to copy that again for stage 3. So stage 3, remember the reason why drag appeared is because because it started to move. Now, because, in fact, we should probably summarize at this point what's happening to the velocity. Well, if here we have the maximum, the highest possible force when it's just equal to the weight, then the acceleration is going to be at its maximum. So even though the velocity is 0, the acceleration is at its maximum. Okay. Now we've got the force is reduced. We're going to say the acceleration has reduced. Right? So yeah, this is kind of the idea that a lot of people sort of struggle with. They say, well, when I let go of something, I don't ever see it just staying there, even for the smallest amount of time. So the idea is it immediately starts speeding up, but it speeds up from 0. So so it's very instant. The very instant you let go of something, it's 0, and then immediately it starts to speed up. So we can say that the velocity is equal to 0 and the velocity is small here, but because it's faster than 0, then it's going to we have a little bit of drag. Now the acceleration has reduced, but it's still accelerating, which means the velocity. Let's use the green one. The velocity has still increased. Now the velocity is high. Okay, and and it's so high, or because it's high, the drag is also high. Okay, because drag is dependent on the the drag is dependent on velocity. Still, just as before, the resultant force, the total force, is equal to the weight minus the drag, just like before. And now in this situation, it's moving so fast that the drag is actually the same size as the weight. It's reached the point that the drag is the same size as the weight. So so we're going to say that, yes. Let's use black. Well, it would move. Yes, if you think about it, we know that it would move because when objects are falling, they do reach. So the thing that does stop is not the speed, but the acceleration. Okay, so we're saying that d is equal to mg, which means that ft is equal to mg minus d. Well, if they're both the same, ft is equal to 0. The total force is equal to 0. No, forces do cause motion, but it's not true to say they cause velocity. They cause acceleration. If we look at Newton's second law, F is equal to ma. So rearranging it, there's no symbol for velocity there, but there is a symbol for acceleration. Acceleration is equal to force over mass. Okay, so if we wanted to rewrite some of these, we could say at the beginning, acceleration is equal to the force over the mass, which is, as you said, just g. So the m's cancel out. In the second case, we would say that the acceleration is equal to the force again, mg minus d, over the mass again. You could simplify that to say it's equal to g minus d over m. And then we have over here, so we got, well, basically acceleration is equal to 0 over m, which is just 0. But that doesn't mean it's not going to move. That just means it's not going to get any faster. It's going very, very quickly. It's just going to carry on going very, very quickly, but not go any faster than it is. So this is a maximum velocity. It's not going to slow down at this point. Yeah, you see. So it's, well, yeah, I suppose. Well, not as if there's no air resistance, because if there's no air resistance, it would carry on speeding up. So, if, for example, if something was falling on the moon, it doesn't have terminal velocity. It just carries on falling because there's nothing to slow it down until it hits the ground, of course. Right? So, if you plotted this graph of, let's say we plotted speed against time for this falling object, it would look like this. So that would be the time. That would be the velocity or the speed. And it would start off going very, very steep because it would have a high acceleration. Right? So it would start off with a high gradient, but then that gradient would start to flatten out until eventually it doesn't get any higher. Now it doesn't go down. There's nothing to slow it down. It reaches a maximum speed. And we can call this the terminal velocity. So I'll just put a little comment there, and I'll terminal, or we should probably say terminal speed, really, is usually, I think that's more accurate, really. Yeah, so that's the terminal speed. So it happens because the faster you get, the more that the drag builds up until the drag is equal to the force that's pushing it forwards. And so you would have different terminal velocities based on the size of the forward moving force, the viscosity of the liquid, and okay, so basically the size of the forward force and then the size of the air resistance, or this, yeah. So I'm gonna rewrite that until it makes complete sense. this terminal, sorry, so it's going to be determined by the surface area of the object. So so imagine if it was really, really thin like a dart, it's going to go flying like. And by the way, it's probably worth mentioning at this point, when I say surface area, I mean the surface area that is facing the direction it's moving. So in other words, if you imagine a piece of paper, right? If the piece of paper was moving downwards at this point, then the surface area would be like the surface area of the edge of the paper. Whereas if it was moving out of the screen, well, the surface area is all this stuff here, so it's going to be a lot harder. So that's why parachutes can fail if they crumple. They may have a high surface area, but if they're at an angle, then that's not going to work, of course. So we don't normally go into that much detail, but it's worth understanding that. So it's the surface area, or how streamlined it is as well. So, for example, if I've got a truck, a very unaerodynamic truck moving through the air, and meanwhile, I can keep that. I can increase the surface area. I can put something like this on it, and that actually increases surface area. It was that high, and I've actually added a bit onto it. But I don't know. Yeah. Anyway, well, that may basically making it more streamlined allows the air to sort of like slide over it more easily, and that means overall it's going to produce less of a resistive force. So then how viscous the substance is, the fluid is, and the size of the propelling force. Now, when I say the size of the propelling force, I'm keeping it general here. I could say the weight, but that would only apply to falling objects. But in that case, weight would be the propelling force. When something's moving down, something's falling, then the force that's pushing it down is obviously the weight or gravity. But things have terminal speeds if they're driving along. So you can't say, so if a Ferrari is driving along at, with the foot halfway down the accelerator, and it will have a terminal velocity, a terminal speed. But that once you put your foot further down on the accelerator, then it will have a new terminal speed. And if you increase, so the terminal speed is that the specific terminal speed depends on the size on these factors, and if you change them, you'll get a new terminal speed. Right. So remember that. So acceleration just means whether it's speeding up or slowing down, right? If it's not accelerating, it's not speeding up, it's not slowing down. That doesn't mean it's stopping. In fact, if it was stopping, it would have to have acceleration, or we would call it deceleration. So it's not going to slow down. It's not going to speed up. It's just going to go at whatever speed it's going at. So if there's so it was already moving when the forces started cancelled each other out. So it just carries on moving at that speed. Okay. Yeah. So imagine a meteor flying through space. There's no motor on that meteor, right? It's just going to fly through space for millions of years. So there's no force applying it. It's not going to speed up. It's not going to slow down. It's going to keep going at whatever speed it's going. The only time it's going to stop is when it hits something, and that when it hits something, that something will apply a force to make it stop or slow down. Okay. So that's why we get to this flat bit. So the speed is constant at that point. So we would call this the terminal velocity, and which is a constant speed. Okay.